Millions of sugar beets enter these factories looking like dirty roots, but inside them waits the same crystal you know as sugar, and here's the surprising part. This entire transformation begins with a vegetable that can contain roughly 1/5 sucrose by weight. You might expect crushing, like a sugarcane mill, but beet factories use hot water to pull sugar directly from sliced roots. But before a single crystal can form, dirt, stones, plant material, and dozens of unwanted compounds must disappear. So imagine following one beet from a field into a factory, where every minute changes its identity. And by the time that journey ends, the humble root will become sparkling crystals ready for kitchens around the world. Sugar beets thrive mainly in temperate farming regions, especially across Europe, Russia, North America, and parts of Asia. In 2024, Russia produced roughly 46.7 million tons of sugar beet, making it the world's largest producer that year. Germany, France, the United States, and Turkey also rank among the world's major sugar beet producers. Unlike sugarcane, beets can travel directly from nearby farms to factories because they grow naturally in cooler climates. That short supply chain matters because freshly harvested beets can lose quality during storage, especially when conditions become warm. When trucks arrive, automated unloading systems rapidly dump tons of roots into receiving areas without stopping the production flow. The first challenge looks simple: clean the roots thoroughly while wasting as little sugar-rich material as possible. Huge quantities of soil can arrive with harvested beets, so screens, traps, washers, and separators remove stones before slicing begins. Then precision knives transform the cleaned roots into thin strips called corsets, dramatically increasing surface area for extraction. This shape is crucial because thinner, more uniform corsets let hot water contact more beet tissue and recover more sucrose. Now comes the hidden trick. Instead of crushing the beet, the factory essentially washes its sucrose out with controlled heat. And that brings us to the factory's first major transformation. Millions of solid roots are about to become liquid. Inside the diffuser, hot water moves countercurrent to the beet slices, allowing sucrose to migrate naturally from tissue into water. A typical diffusion process runs around an hour, with water near 70 degrees Celsius carefully controlled for efficient extraction. The result is raw diffusion juice, carrying dissolved sucrose along with proteins, minerals, color compounds, and other non-sugars. But this juice looks nothing like table sugar, and it is nowhere near clean enough for crystallization. First, screens remove remaining pieces of corset, then heaters raise the juice toward roughly 85 degrees Celsius. Then the factory adds milk of lime, creating strongly alkaline conditions that help gather troublesome impurities together. In conventional purification, the juice can reach very high pH, sometimes above 12.6 during liming. Now the real chemistry begins, because carbon dioxide reacts with the lime and forms tiny calcium carbonate particles. Those particles act like tiny cleaning agents, capturing many unwanted materials so filters can remove them from the juice. The clarified liquid becomes dramatically brighter, while a thick stream of lime mud carries away the captured impurities. A second carbonation stage can remove remaining lime and impurities, pushing the juice closer to crystallization quality. Instead of boiling everything at once, factories use multiple evaporation stages to recycle heat and remove water efficiently. Steam generated in one effect can help heat another, turning waste heat into useful energy instead of simply losing it as water disappears. Thin juice becomes thick syrup, and its sugar concentration climbs toward the conditions needed for crystal growth. Typical systems can concentrate purified beet juice through several effects until thick juice reaches around 65% dry matter. But thick syrup still isn't sugar, because the sucrose remains dissolved until engineers force crystals to appear. Under reduced pressure, water can evaporate at lower temperatures, helping concentrate syrup while limiting unnecessary thermal damage. Tiny seed crystals provide starting points, then dissolved sucrose attaches to their surfaces and builds larger white crystals. The mixture now looks like wet snow, with countless sugar crystals suspended inside concentrated mother liquor, and this is where the factory finally separates the crystals from the liquid surrounding them. Centrifugal force throws the liquid outward while sugar crystals remain against the spinning basket, producing remarkably clean granules. The separated crystals then receive controlled washing, drying, and cooling until their surface becomes dry, bright, and free-flowing. What started as a dirty field crop has now become refined crystalline sucrose, but the factory still isn't finished. Modern beet factories don't simply watch machines. Sensors continuously monitor temperature, flow, pressure, concentration, and product quality. Near the slicing station, precision systems watch cassette size because inconsistent slices can reduce extraction efficiency. If slices become too thick, extraction slows. If they're damaged, unwanted material can enter the juice more easily. During purification, sensors help operators maintain narrow operating conditions so chemistry removes impurities without unnecessarily sacrificing sucrose. The carbonation stage is especially important because poor clarification can make later evaporation and crystallization much harder. Then the evaporator station becomes the factory's thermal heart, concentrating thousands of liters while recycling energy between effects. Some large evaporator installations contain tens of thousands of square meters of heating surface across multiple effects. At crystallization, control becomes even more delicate because supersaturation must encourage crystal growth without creating unwanted tiny grains. Too much supersaturation can create excessive fines, while too little can leave valuable sucrose trapped in the mother liquor. Once crystals reach the desired size, centrifuges spin them at high speed to separate solid sugar from liquid. Here, human judgment still matters, because experienced operators can recognize subtle changes in crystal behavior that instruments don't fully explain. That human-machine partnership continues through final screening, where oversized crystals, dust, and foreign particles must be separated. Samples are also tested for moisture, color, crystal size, purity, and other specifications before the product reaches packaging. The goal isn't simply white sugar, it's consistent sugar that behaves predictably in food production, baking, beverages, and kitchens. Finally, the finished sugar enters controlled storage, where dry conditions prevent moisture from turning free-flowing crystals into stubborn clumps, and just when the process seems complete, the numbers reveal how enormous this global beet-to-sugar machine really is. In 2024, global sugar beet production reached roughly 310 million tons across farms on several continents. Europe alone accounted for more than 197 million tons, showing how deeply beet sugar is tied to temperate agriculture. Russia led individual countries at about 46.7 million tons, followed by Germany at roughly 36.7 million tons. France produced about 32.6 million tons, while the United States reached roughly 32 million tons that year. Turkey followed with roughly 23 million tons, highlighting how beet sugar production stretches far beyond Western Europe. Poland, Egypt, Ukraine, China, and the United Kingdom also appear among major beet-producing countries. One cooperative example shows that 100 tons of clean sliced beets can yield about 110 tons of raw juice and wet pulp streams. The leftover pulp doesn't simply become waste. Factories commonly press, dry, and pelletize it for animal feed. Even lime mud and other byproducts can enter recovery pathways, reducing the amount of material that leaves the factory unused. Historically, beet sugar helped Europe build a domestic sugar industry when imported cane sugar became expensive or difficult to secure. Over roughly 2 centuries, the basic pathway survived, while automation, energy recovery, sensors, and process control transformed its efficiency. Today's factories also chase energy efficiency because evaporation and crystallization demand enormous amounts of controlled heat. That is why multi-effect evaporation matters. It can reuse steam energy instead of demanding fresh heat at every stage. And now comes a surprising comparison. The same basic chemistry can turn a field of roots into thousands of tons of finished crystals. Did you know the beet itself isn't crushed into a sugary paste? The factory extracts its sucrose mainly through diffusion. Did you know beet pulp can become animal feed after the factory removes most of its valuable soluble sugar? And did you know some modern beet factories process thousands of tons every day during the harvesting campaign? The future challenge is squeezing more sugar from every ton while using less water, less energy, and creating fewer losses. Advanced sensors, membrane technologies, improved heat recovery, and smarter control systems could further reduce resource use in coming years. But even with advanced technology, the journey still depends on one thing that existed long before factories: the beet itself, and that is the final mystery. How does something pulled from soil become a crystal that looks almost completely unrelated? The answer is not one machine, but a carefully connected chain of farming, washing, slicing, extraction, purification, evaporation, and crystallization. Every stage removes something unwanted or concentrates something valuable until almost everything surrounding sucrose has been stripped away. The factory doesn't manufacture sucrose from nothing. It reveals, concentrates, purifies, and crystallizes what the beet already stored. Even the water surrounding those molecules becomes part of an engineering puzzle, because removing it consumes significant thermal energy. That is why the quietest parts of the factory, hidden pipes and heat exchangers, can matter as much as giant machines. Meanwhile, thousands of sensors quietly make thousands of tiny decisions, keeping temperature, flow, pressure, and concentration within operating limits. And when something drifts outside specification, alarms, controls, and experienced operators work together before the final sugar is released. The final crystals may look simple, but each grain represents hundreds of controlled movements across a massive industrial system, from a farmer's field to a kitchen spoon. The material may travel through dozens of carefully controlled operations, and somewhere inside that journey, the muddy vegetable disappears completely, leaving behind something almost impossibly clean and familiar. That transformation is why sugar beet processing remains one of the world's most fascinating examples of agricultural engineering. And now, we can finally follow one last beet all the way from soil to finished sugar. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.